Hello, I'm Rishikeshwar. I'm going to present on a topic ultrasonic testing. Ultrasonic testing is a NDT method. That is, NDT stands for the testing of a material without destroying its property. And in NDT, we have various methods, and UT is one of them. And in UT, we use ultrasonic waves to detect or check the material. Now, ultrasonic testing have various applications, including in various industries, including steel and aluminum construction, metallurgy, manufacturing, aerospace, automotive, and other transportation sector. It can be even done in concrete and wood, other than metal alloys and steel. So it has various applications in various industries. This image shows the man testing using ultrasonic waves. Now, history. Soviet scientist Sergei Vyshyakolov is considered the father of modern ultrasonic testing. He successfully demonstrated in 1928. So UT plays the major role in World War II. And now basic principle of ultrasonic testing: acoustic impedance mismatch, that is the difference in the sound resistance of the material. Now ultrasonic testing uses high frequency sound wave, that is more than 20 kHz. Now, acoustic impedance depend on the density and the velocity of the material. As we know, the human audible range is 20 Hz to 20 kilohertz is the human audible range, and over the human audible range, we name it as ultrasonic, and below the human audible range, we name it as infrasound. Is the basic principle of UT is acoustic impedance mismatch. We need ultrasonic sound to test the material. So ultrasonic sound, that is 20 megahertz and more. Now the property of ultrasonic wave, they are wavelength, frequency and velocity plays a major role. Now modes of wave propagation, that is longitudinal wave or compression or density waves. Now transverse or shear waves, surface or Rayleigh waves, plate or lamp waves. These are the four types of modes of wave propagation. Now we're gonna see about longitudinal waves. Longitudinal waves are the waves which the vibration are parallel to the direction of wave travels. The displacement of the medium is in the same and direction opposite to the wave propagation. And velocity of longitudinal wave in steel is approximately 5940 meter per second, and it can be used to detect the base metal, inspect the defects parallel thickness of the material, and it cannot be used in weld metals and to detect angular and perpendicular surface, because longitudinal waves does not travel in other directions. And these are the materials and their speed of sound which travel in that material is given in the chart. And now we're gonna see about transverse waves. Transverse waves travel in perpendicular to the direction of waves advances, and the velocity of transverse wave is 3240 approximately meter per second. And transverse waves are used to detect the angular defects of the weld scan, and it cannot be used to find material thickness, because this is the difference between the longitudinal waves and transverse waves. Now longitudinal waves uses the compression and relaxation motion, that is look at the direction of travel in the image. And now transverse image uses that thrust and throw. Now surface waves is a mechanical wave that propagates in the interface between the different media. This is a surface wave image, that is example the waves in the ocean or surface waves. Direction of propagation and particle motion. Particle motion is a elliptical motion. Now lamp waves are travel in both side of the material. These are two types, symmetrical and asymmetrical. and this shows the asymmetrical and symmetrical amplitude. Now sound at interface. Interface is the boundary between two medium. Some of the sound will transmit and the remaining will reflect in the boundary between two medium. And wholly it is depend on the acoustic impedance of the two materials. And look at the image where the incoming sound hits the acoustic barrier. Some of the waves are reflected back and some are transmitted into the other material. Now we're gonna see about acoustic impedance. It is the resistance of sound propagation and it is defined as the density multiplied by sound of the material, speed of sound of the material. Now percentage of transmitted through the material and percentage of waves reflected back to the initial material is equal to 100%. Now this is a chart which shows the different materials acoustic impedance. That is aluminum, copper, steel, titanium, oil, water and air. Now reflection of sound waves. As we all know, bouncing back of sound waves from the surface is called reflection of sound. And loss of reflection or incidence angle is equal to reflection angle. The incident wave, reflected wave and normal at the point is the same plane. Now this is the reflection angle image. That is incidence angle and reflection angle are equal. Look at the property of reflection of sound waves. And reflection and transmission coefficient is nothing but the ratio of the amplitude of reflected wave to the incident wave is reflection coefficient, and the ratio of amplitude of transmitted wave and incident wave is transmission coefficient. Now this image shows the formula of percentage of transmission and percentage of reflected waves. Now attenuation of sound waves. Attenuation of sound waves is the loss of intensity of ultrasonic beam. It has three types of losses, that is interface loss, absorption loss, scattering loss. The refraction of sound waves, that is the change in direction of wave when it passes through one medium to another. It is wholly depend on the Snell's law. The Snell's law we're gonna see in the next slides. Now this image shows the refracted wave and attenuation and reflected wave when the incidence rays passes through medium 1 to medium 2. The diffraction of wave is a difference in the initial path to the final path after the wave passes through opening or barrier. Now Snell's law, that is sin I by sin R equal to V1 by V2. That is sin I is the incidence ray angle and sin R is refracted or reflected angle. Now V1 is the velocity of the sound in first material and V2 is the velocity of sound in second material. Now in the next slide we're gonna see about critical angle. Critical angle is the arrival angle at which when the sound is traveling from one medium to another medium, the refracted wave is travels in the interface of the two media, and that angle is called a critical angle. Example, look at the image when the denser medium ray is traveling from denser medium to less medium, the refracted wave traveling in the interface of the two material. This is called a critical angle. First critical angle and second critical angle we're gonna see. First critical angle is when the refracted wave, that is longitudinal wave, is refracted in the interface of the both surface, that is called first critical angle, and when the shear wave is refracted in the interface of the two material, it is called second critical angle. The first critical angle calculation, there is example, we take steel as a medium 2 and Fairfax as medium 1. The critical angle is 27.6 degree first critical angle and the second critical angle is 57.7 degree. Now piezoelectric effect. It is a process of using crystals to convert mechanical energy into electrical energy, and reverse is vice versa. It is a process of using electrical energy into mechanical energy. This image shows the reverse piezoelectric effect. That is, electrical signals are used to produce mechanical waves, that is, sound waves. This is the difference between piezoelectric effect and inverse piezoelectric effect. Piezoelectric effect uses the input strain to produce output voltage, and reverse piezoelectric effect uses the voltage input to produce strain output. Now, types of piezoelectric material depends on crystal cutting. We have X-cut crystal and Y-cut crystal. X-cut crystal produces longitudinal waves, and Y-cut crystal produces shear waves. This is the diagram shows the X-cut crystal and Y-cut crystal. Now, depend on the material nature, we have natural crystal and artificial or polarized crystal. Natural crystals include quartz crystal and lithium sulfate, and artificial crystal can include barium titate, lead zirconate, ceramics, lead methanibate, lead niobate, and lithium sulfate. And the temperatures are given near the names. Now, test techniques. They are pulse echo method and through transmission method, which is depend on the number of transducers used and the receiver and emitter transducers. And contact and immersion testing is depend on where the transducer is placed over the material or above from the water. First, we see about pulse echo method. Pulse echo method is same transducer is used for emission and receiving the sound wave. It uses the y-axis as when the result is shown. It uses the y-axis as the amplitude of reflection intensity, and the distance or time is taken as a x-axis. This is an image of pulse echo method. That is, a transducer is used to emit and receive the echo and pulse. Now, through transmission method, it is used to it is used by emission of waves is emitted by different transducer, and a different transducer is used to receive the sound energy in the opposite side of the material. It is tested by it is shown in the image by that is the it is a reduction of intensity of the wave is seen to detect the defect, and contact ultrasonic testing, that is the transducer is placed above the material or specimen which is reachable, and we use couplant above the material in between the material and transducer. This is the image shows the contact method. Now, immersion ultrasonic testing. It is a method used when the material is placed inside the water or water couplant, where we use water couplant and such unit is placed above the water, and transducers, which are the material which is a device used to convert electrical pulses into mechanical pulse vibration, and mechanical vibration is converted back into the electrical energy. And we have various types of probes. That is, probes is also called as transducers probes. We have normal probes or zero probes or longitudinal probes, shear probes or angle probes. And third, transmitter receiver probe are also known as dual crystal probe. First we're gonna see about normal probe. Normal probe, it contains single crystal and produce longitudinal waves. The sound energy produced is perpendicular to the surface. And in angle probe, we have various type of angles, that is 35 degree, 45 degree, 60 degree, 70 degree and 80 degree. This is depend on the material thickness. We choose the angle depend on the material thickness. They produce sound energy at an angle to the surface. Now this is the normal probe, and this is how the flaw is detected in normal probe. And this image shows the detection of flaw using angle probe. Mostly well scans are in well scan the flaws are detected using angle probe. And dual crystal probe also produces longitudinal wave as such in normal probe, but it does not generate initial echo and echoes are not clear. Now, this is the difference between single element transducer, that is normal transducer, and dual element transducer. Now, measurement normal beam inspection used to measure thickness of the material, inspect the base metal, inspect the defects parallel. And TR probe, that is dual crystal probe, used to find surface parallel defects or for lamination check. Now the angle probe inspection is used to measure over the well scan to inspect defects angular or perpendicular to the surface. This is the difference between longitudinal wave direction and shear wave direction and detection of couplant. This is couplant is a material that facilitates the transmission of ultrasonic energy from transducer into the test specimen. It is necessary to remove the air gap and also used to give smooth movement for probes. Now electromagnetic acoustic transducer. This transducer does not need any couplant, and this does not depend on the piezoelectric effect. It uses the electromagnetic mechanism, that is electrical energy and mechanical energy is used to produce the sound waves. As such in the next image, that is this image shows the visual difference between piezoelectric ultrasonic testing and electromagnetic ultrasonic testing. Now pulsar receivers. Pulsar receivers are the device which has two units, that is pulsar section and receiver section. Pulsar section generate amplitude of electrical pulses which are ultrasonic converted into short ultrasonic pulses when applied to an ultrasonic transducer. In the receiver section, voltage signal produced by the transducer, which is represent the received ultrasonic pulses. Now this is the device which connects ultrasonic transducer and display scope. Data presentation can be collected and displayed in number of different formats. We have A scan, B scan and C scan, and each presentation mode provide a different way of looking. First we see the A scan. A scan presentation displays the amount of received ultrasonic energy as a function of time. And B scan, which shows the cross-sectional view of the test specimen. This image shows the A scan presentation and B scan presentation. And C scan presentation provides a plane type view of the location of material and size of the test specimen. This image shows the C scan presentation. Now calibration of the material probes. Calibration refers to the act of evaluating and adjusting the precision and accuracy of ultrasonic flaw detector. Calibration blocks. We have calibration blocks to calibrate the devices. Calibrating the normal probe is by the above image. We're gonna calibrate these types of methods, and the calibration of angle probe. We need to follow this use 100 millimeter curvature range, minimum 100 millimeter and range 100 millimeter. These are the requirements. And now V1 calibration block refers to determine the index point of ultrasonic oscillation. These are the 5 points we need to do using the V1 calibration block. Now V1 calibration block, this is V1 calibration block which is standard all over the international, and this is V2 calibration block which refers to calibrate the floor detector sweep by sound velocity during operation with straight beam probes. Calibrate the floor detector sweep by sound velocity during operation with angle beam probes. These are the four methods. And determine the probe angle of sound wave in steel. This is V2 calibration block, which is also a standard all over the international. And this is the dimensions of V1 block and V2 block, which cannot be changed. And this is distance amplitude correction curve. This curve is a method of compensating for the fact that the pulse echo response of the reflector will decrease as the distance of the reflector from the ultrasonic probe increases. This image shows the DAC curve. The y-axis amplitude and take range as x-axis. Now ultrasonic testing have various advantages, and some of them are internal defects can be detected and sized. Thick specimens take no more time to examine than thin ones. Only one side of the component is needed to test the IoT, and no radiation hazard. Unlike RT method, UT has no radiation hazard, and volumetric and crack-like defects can be detected irrespective of their orientation. Now, some very small disadvantages for UT include a high degree of operation skill is needed for the technicians to perform UT. And in certain metals like arsenic steel, the large grain size is found. So we cannot find the distant difference between attenuation and the defect or discontinuity. Spurious indications and the misreading of signals can result in unnecessary repair of the devices. Now we're going to see the video for a better understanding of ultrasonic testing.
It is possible to investigate whether there are discontinuities under the surface using ultrasonic sound waves. Ultrasound has such a high frequency, people cannot hear it. The vibrations can, however, be measured with sensitive measuring equipment. Using this storage vessel, a weld is checked for internal discontinuities. First, the object being examined must be cleaned and free of any material that may interfere with the exam. Simply said, it works as follows. Sound waves are transmitted into the material with the transducer, and an echo is sent back from the rear wall or discontinuity. By registering this echo, we can deduct the thickness of the material, or if a discontinuity is present. In case of a discontinuity, sound is echoed back faster. Thus, we can see if the material wall is thinning, for instance by corrosion. The examiner first applies a contact fluid to enable the ultrasonic feeler to make proper contact with the material. This bonding layer serves to conduct the sound waves into the material. Without the contact fluid, they would immediately bounce back from the surface. A transducer converts an electronic signal into ultrasonic sound waves. It can both send and receive. The ultrasound equipment captures the reflected waves and converts this into a visual signal. This enables the examiner to see whether there are any discontinuities. If there is an indication, the exact location can be determined using calculations. It is possible to investigate whether there are discontinuities under the surface using ultrasonic sound waves.
And thank you.